Alright, let's take a look at three brothers. You have the integral remainder, alternating series remainder, and way down here you have Lagrant Error bound. Now they all find one thing, error, the ability to determine just how accurate a series can be. So what I would like to do right now is just take a look at what the differences between them. Now you may recall for the integral remainder theorem, it's a way to determine just how accurate a problem like this can be. A series like this to be. We want to approximate the sum of a series by using 6 terms. So we got this series right here. We want to approximate it by using 6 terms. So if I wanted to do something like that, it would be s of 6 equals 1 over, what's that? Let n be 1 cubed plus 1 over 2 cubed, just like me, 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed plus 1 over 6 cubed. And I can approximate that. Now a real quick way on the calculator is just to type this in as the sum of a sequence, like so. And I would just type in, what's that, divided, 1 over n cubed, so x to the third. And I would type in comma x, whoops, not w, comma x, comma 1, comma 6, the first series. And I would get this number right here. 1.1903. And I want to know just how accurate this is, dot, dot, dot. How accurate? In other words, what's the error going to be? So, according to the integral remainder, as you may recall, to get the error on these, all we're going to do is, we would say that the remainder of the 6 terms has to be greater than or equal to 0, but less than or equal to the tail end of all of the rest of them, 6 to infinity of 1 over x cubed dx. Basically, it says that my error has to be between 0, the most I can be off is 0, and the sum of everything else. This is sometimes called the tail. In other words, it's all the other terms added up, okay? And we would solve that by using limits, of course, the limit as b goes to infinity, and of, what's this, 6 to b, and if I integrate this, this just becomes very quick, what's that, x to the negative third, so we would get negative, 1 over 2x squared, like so, and if I solve this, the limit as b goes to infinity, we would get negative 1 over 2b squared plus 1 over, 2 times 36. So this goes to 0, and this becomes 1 over 72. So we're saying that the error, that our remainder, has to be between 0 and 1 over 72. So if I want to approximate it, my actual sum will be s minus 1.1903. is going to be greater than 0 or be less than or equal to 1 over 72, and I would solve this. And that's the integral remainder. We didn't like that one. Takes a long time. But then we have the alternating series remainder. Now the alternating series remainder was a little bit easier. It says if the series alternates, decreases, and has a limit of 0, then we would know that to get the remainder, the error is going to be less than the next term. Well, here I have a series. It's alternating. It's going to be decreasing over time, and the limit will equal 0. So if I wanted to solve the same one, well, s sub 6 equals, now in this case right here, it's almost the same, but when I type it in, I have to make this a negative 1. So I'm going to do the same type of problem. Hello, where'd you go? There you are. Negative 1. Negative 1 to the x, comma x, parentheses, caret x, and I hit enter. But now my sum here, my first 6 terms, is going to be this negative 0.8998. There's my approximate sum. Now, because this series alternates, decreases, and it has a limit of 0, we know to get the error of the 6th term, it's just going to be less than the next term, a sub n plus 1. Well, how do I get my next term? I just plug it in. In other words, this is going to be less than or equal to the 7th term, which is just 1 over, 7 cubed, which equals 1 divided by 7 to the third, 0.003. So what happens is the most I'm going to add is 0.003. So to get my sum here, it's going to be s minus the approximate, which is this, becomes this, what's that, negative, so that becomes a positive 0.8998, has to be between negative 0.003 and positive 0.003. And again, I would solve this. Now, what you want to be careful of, remember this is my s sub 6 right there, that's my approximate sum. What you want to be really careful with in problems like these, and if we take a look up here, is in both the integral remainder and the alternating series remainder, we have to be able to somehow get the next term. We have to be given a general part to it. We have to be given a general function of sorts to get the next term in my sequence, or series here also. So both of them have a nice little formula. Now, if it's not alternating, we use the integral. If it is alternating, we just use the next term. Lagrange, if you remember, Lagrange said, well, what if we can't get the next term? So here we have one. Let f of x equal sine of x. And we want to write a second degree Taylor polynomial with center 0. Determine the interval for which the value of sine of 0.1 will lie. So we want to approximate sine of 0.1, and we want to find the interval for which it lies. So basically what we do is we have to use our derivatives. I'm going to use the old-fashioned way. F of x is sine of x. So the value, sine of 0 is 0. F prime of x is cosine of x. Its value at 0 is, the derivative, it's 1. And the second derivative of x is sine of x. And its value, of course, is also 0. Now, because I'm going to use Lagrange, I'm going to need the next term anyways. The third derivative is negative cosine of x, and of course, its value at 0 is negative 1. I want to write my second degree Taylor polynomial, so here we go. Matter of fact, I really can't write it in this case, so let's change this up a little bit. Let's write a third degree polynomial, okay? So we'll need the fourth one, so we'll talk about that in just a moment. So I'm going to change it up a little bit. So my p sub 3 of x will become 0 plus, remember, my Taylor polynomial, 1, and this is times x to the first, minus x cubed over 3 factorial. And there's my third degree Taylor polynomial. Now I want to find out just how accurate is that sine of 0.1. So to get that, I need my fourth derivative. So there's my third degree Taylor polynomial. And now I want to talk about the remainder part, the error. Remember, for a Lagrange, since I don't know what the next term is, or in this case I do, but pretend we don't, so we're going to use our Lagrange error, which says we look at the value of the nth plus 1 derivative, the maximum it can be, over n plus 1 factorial times x minus c to the n plus 1. So to get the remainder, we're going to be less than that. So my remainder of my third term, in this case, is going to be less than, and remember right here, the value of the fourth derivative of z over 4 factorial times c is 0, x to the fourth. It becomes less than or equal to because it could possibly equal that one in that case. So our question here is we need to find the maximum value of the fourth derivative. Well, to do that, I have to take the fourth derivative. Well, my fourth derivative of x is negative sine of x. Well, it's sine. What's the maximum value sine can be? Yeah, 1. Its max value is 1. So that's what goes here. So my remainder of my third is going to be less than or equal to 1 over 4 factorial, which is 24, times x, that's my 0.1, to the fourth. And I can just type that in. My calculator, here we go. Whoop, oh, there we go. 1 divided by 24 times 0.1 to the fourth. And I get, wow, look how accurate that is. 0.00001. How many zeros? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 4. So there's how accurate that term is going to be. Right there. That's how accurate we are going to be when we try to approximate sine of 0.1. All right. Just a quick little review. Thank you. Bye-bye. Good luck.